The sample covariance is that average written out, 1 over n minus 1 times the sum of the products of deviations. A positive value signals a positive relationship, a negative value the opposite, and 0 means no linear relationship. Why divide by n minus 1 rather than n? Hold that thought. The reason belongs to Chapter 3. But covariance has an awkward feature. Its sign is meaningful, its magnitude is not. Measure price in thousands rather than millions, and the covariance inflates 1,000-fold with nothing real having changed. So the size of a covariance cannot be compared across datasets. The fix is to divide by the standard deviations of both variables, which removes the units entirely and yields Pearson's correlation coefficient. The standardization needs the sample variances, the average squared deviations of each variable, and their square roots, the standard deviations. For our data, the mean apartment size is 65.3 square meters and the mean price 2.11 million kroner. With the means, the standard deviations, and the covariance in hand, we can standardize the covariance. Pearson's correlation is the covariance divided by the product of the two standard deviations. It always lies between -1 and +1, where the endpoints mean a perfect linear relationship and 0 means none. It is symmetric in x and y and scale-free. For the apartment data, it comes to 0.27, positive but far from 1. The size and price relationship is real, yet far from deterministic. How should we read 0.27? Larger apartments generally cost more, but the exceptions are everywhere. Some apartments above 100 square meters sell below 1 million kroner, and some small ones fetch up to 5 million. The table gives a rough vocabulary. Below 0.1 negligible, up to 0.3 small, then moderate, large, and very large past 0.7. Rough conventions only. Context decides what matters. The R implementation reads the data, keeps complete cases for living area and price, and builds the correlation from its ingredients, the two means, the covariance, and the two variances. It then checks the manual result against the built-in correlation function. Both give roughly 0.27. In practice, you will simply call the built-in function, but computing the coefficient once by hand fixes the formula in memory. The Python version mirrors it with pandas and NumPy. Drop the missing values, compute the means, assemble the covariance and variances, divide, and compare with the built-in correlation method. Same answer, roughly 0.27. This side-by-side pattern, R and Python producing identical numbers, repeats through the whole course, and it is a habit worth copying whenever you switch languages. Now an important limitation, drawn rather than stated. The scatter here bends like an arch, unmistakable covariation, yet Pearson's correlation is essentially 0, about 0.035. Pearson measures linear association only. A perfect deterministic curve can still produce a correlation near 0. Hence, the rule at the bottom, draw the scatter plot before computing any correlation, because the coefficient can be 0 even when a strong relationship is staring at you.